Good day and welcome to part 4 of our discussion on the definite integral. As indicated in the previous video, I wanted to go over one more example using the definition of the definite integral. And I will note that this problem can be worded in multiple ways. We could simply ask you to use the definition of the definite integral, or instead we could give it this more geometric flavor. Find the area enclosed under the graph of some function between two values of x. And note, regardless of how we word this, what we are asking you to do is evaluate the definite integral from 2 to 5 of 1 plus x squared. And note, it has that nice interpretation of an enclosed area because the graph of 1 plus x squared is always positive, so it most definitely is between 2 and 5. Whatever answer we come up with in the end should be a nice positive value. So let's go ahead and evaluate. My first step, as I've indicated before, is to take the time and actually write this as a limit of the Riemann sum. So I'm starting off keeping this as general as possible so that I'm doing, smaller steps, at least in the beginning here, to make sure I don't make a silly mistake right from the get-go. So in this case, we know that our delta x is going to be b minus a over n, so 3 over n. X sub I is equal to a, that lower limit of integration, plus I delta x. So I'm going to write this as 2 plus 3I over n. And then we need f of x sub I. That requires us to take this expression for x sub I and substitute it in for the single x in the equation of the function f. So f of x sub I is 1 plus the quantity 2 plus 3I over n squared. And depending upon the problem, I sometimes prefer to do this algebra to the side because it's less to write down the algebra here than it is to copy every single part of this equation at each step. But I'll leave it to you as long as you do so using good notation and correctly. So in this case, if I expand this out, think foiling it algebraically, we would have 4 plus 2 times 2 times 3I over n, which is going to be 12I over n, plus that quantity squared, so 9I squared over n squared. So substituting this in to our summation now, we would have that this is the limit as n approaches infinity, the sum from I equals 1 to n. F of x sub I is 1 plus 4, which is 5, plus 12I over n, plus 9 over n squared I squared, all times delta x. So then we go ahead and we take this 3 over n and we distribute it through and let it hit each term. And when we do that, we will have the limit as n approaches infinity, the sum from I equals 1 to n, 15 over n, plus 36 over n squared, I, plus 27 over n cubed, I squared. So once again, a nice, slow, incremental process. But from a overall procedural perspective, what you should hopefully be noting is that every one of these problems feels essentially the same stepwise or procedurally. What changes really is the function we're dealing with in the interval, i.e., this a and b value, vary. So continuing on exactly as we've done previously, we will now take this summation and we will break it up over the additions and pull out the constants. So I'm going to write this as 15 over n, the sum from I equals 1 to n of 1, plus 36 over n squared, the sum from I equals 1 to n of I, plus 27 over n cubed, the sum from I equals 1 to n of I squared. And what I'd like to ask you to do now is, if you have not already solved this problem before even starting the video, as I suggested, how about you pause the video now and just finish up these remaining 2 steps. And hopefully you've done so. So now let's take care of these summations using common formulas. The sum from I equals 1 to n of 1 is simply n. That's convenient. Plus 36 over n squared times the sum from I equals 1 to n of I. N times n plus 1 over 2. Plus 27 over n cubed times the sum from I equals 1 to n of I. So n times n plus 1 times 2n plus 1, all divided by 6. And lastly, we need to go ahead and take this limit, but as we've done previously, we'll just think about this term by term, as the limit of the first term is simply a constant, and the remaining two terms are rational functions in n that have the same degree in the top as they do in the bottom. So it becomes a matter of dividing leading coefficients. So 15 from the constant. In that first term, note the leading coefficient in the top would be 36, and in the bottom it is 2. So 36 over 2, or of course we could write 18. And then note in this second term, or third term I should say, the leading coefficient in the top has to take into account that 2. So it would be 27 times 2, which is 54, divided by 6. And I am 100% happy if you leave it in this form. This is a number. It represents the value of this definite integral. Taking it any further, once again, is just kind of purely arithmetic, but just for fun, right? 15 plus 18 plus 9 is 33 plus 9, so 42 represents the value of this definite integral. So for now, this will be the last time together we go through and use the definition of the definite integral, but be prepared, it is something you will certainly see again in the future. So make sure that you're practicing examples. If you have questions, do not hesitate to reach out. In the next video, we will continue our discussion by exploring properties of the definite integral. So stay tuned, take care.